next we're going to look at kind of how to be able to solve some problems. So let's take a look at kind of a different question with exponential equations. If you have a problem where the numbers work out pretty nicely, when we talk about solving equations, sometimes you have friendly numbers like this, where if you look at 2 to the x equals 8, hopefully that's pretty obvious and doesn't take a lot of work to know that x should be 3. 2 to the third is 8. But the problem is sometimes numbers aren't all that friendly in math, and so you might have something like 2 to the x equals, let's just change the 8 to a 9, I guess. So 2 to the x equals 9. Now all of a sudden it's not 3. 2 to the third is 8. 2 to the fourth is 16. So it's got to be somewhere between 3 and 4, but saying it's between 3 and 4 is not very precise. And if you look back to the last example when we're talking about money, if you want to really be pretty accurate to talk about your money, like if you're in a business field, it's pretty important to be precise and not just say, oh, it's kind of between $10,000 and $100,000. You might want to have a pretty precise value in there. And so you can think about kind of how do you be able to find what specific value of x you have, such that 2 to the x equals 9. That's not necessarily an easy problem to work through, and so for that we need a new kind of a function. And so we need to introduce the logarithmic function, which is going to essentially undo the exponential function and take that x value that's up in the exponent and bring it down so that we can solve for x without having to hope we get close enough. Exponential functions and logarithmic functions are inverses of each other, and so I want to just highlight that one property of inverse functions is that when you graph them, they should be symmetric across a specific line. We've learned about this somewhere else, but here's the line y equals x, and inverse functions should be symmetric across that line. So when you graph an exponential function, let's look at one we actually had earlier, f of x equals 2 to the x, the graph would look something like this, and it would just go up and continue increasing very quickly. And so the logarithmic function that's supposed to be the inverse of that, which, remember, the base of the exponential has to be the same as the base of the logarithmic function. So this would be the function log base 2, because the exponential had a base of 2, of x. This function is going to be symmetric across that line y equals x. And so that function is going to look kind of like this and behave very similarly, but across that line of symmetry there. And so we can use the log with a certain base, and notice that where the x is in the log function is inside of the parentheses. So it's pretty common for us to have something like the log base 3 of x plus 1, or log base 10 of x minus 4, and notice where the x's are is usually inside of the parentheses there. In that case, it's helpful for us to be able to try to convert from having logarithms to kind of an exponential form. And so here's kind of the main way we want to do that. The way that a logarithmic function is defined is to say the log base b of x, and you could actually replace f of x with y. I'm just going to cross this out, because a lot of times we use f of x now instead of y, but the way we first learned about f of x is just replacing the y. And so if you think about where the y is and where the b is and where the x is, you can convert back and forth from the logarithmic equation on the left to this exponential equation on the right that says b to the y equals x. And so on the left you have a logarithmic equation. On the right you have an exponential equation, and these two equations mean exactly the same thing. So this kind of an identity here helps us be able to convert from one form to the other. If we have something like 2 equals the log base 3 of x plus 1, kind of looks a little bit like something we had earlier. You can convert this to the exponential form and to be able to solve for your variable by taking the base down here. Remember, that's where b was. And it would look like 3 is supposed to be the base of the exponential raised to the 2 power equals x plus 1. And if you kind of forgot where those letters are, go back to the last screen where the last shot where you see kind of where the y and the b and the x are, and make sure that you have them in the right spot, because the location of those is very important. Or if you had a problem like 3 raised to the x plus 1 equals let's say 50, here's an exponential equation. We're trying to say what exponent do you need in order to make this to be a true statement? What value of x do you need to plug in? We would have something like, we could transform this into being the log base 3 of 50 equals x plus 1. And again, make sure you keep in mind where the x and the d and the y are in those equations, because the placement is really important. And so being able to go back and forth from the exponential equation to the log equation and from the log equation to the exponential equation is pretty important. Let's look at go back to kind of our practical example of money for a second. Let's say we have this equation that says, we're using t. So f of t equals 3,000 times 1 plus 0.02 over 4 raised to the 4t. And here's our function that talks about how much money are we going to have in our account after a certain amount of time. Well, earlier we asked the question, how much money will you have in 4 years? And that's all well and good, but sometimes you want to know how long it will take you to get a certain amount of money. Maybe you're saving for retirement and you want to know how long will it take you to get to a certain point. Well, you might say something like, well, when will I have $5,000 in my account? $5,000 represents an amount of money, not a time, so you don't plug that in for t. You plug it in for f of t. And so then the question would be, how do you figure out what t is? How do you figure out how long it takes for you to get to that amount of money? And so you can divide both sides by 3,000 and kind of work your way to being able to solve for t. This is 5 over 3 on the left side when you reduce that fraction. And remember, the decimal on the inside was 1.005 raised to the 4t. And so you could rewrite this in that log form. You could say, well, this means that you have a log base 1.005 of 5/3 equals 4t. And then if you divide both sides by 4, you could solve for t. Now, you don't necessarily know what all this stuff on the right side means. The log base 1.005 over 5/3. It's kind of like, is that a year? Is that 10 years? Is that 50 years? Is it 100 years? I don't really know, so that's what we're going to talk about in just a minute. But we can at least, now we've kind of solved for t, or we can solve for t. Where before it was up in the exponent and we really didn't know what to do with that. So logarithms are really helpful for us to be able to solve equations when we have a variable up in the exponent.